Hello students, welcome. Previously, lesson 4, form 4, topic 4, we were dealing with the first use of the standard electoral potentials, which was comparing the oxidizing and the reducing power of substances. So today, lesson 5, we want to proceed to the second use of the standard electoral potentials, which is determining the EMF of a cell. So we are saying we can use the electrochemical series to calculate the electromotive force, that's the EMF, of any cell consisting of any two half cells. And we're saying this can be done using the formula. The EMF of a cell is obtained by E reduction means E oxidation. E reduction is the standard electoral potential value for the substance that undergoes reduction minus the standard electoral potential value for the substance that undergo oxidation. So we can have several formulas where we can say the standard electoral potential value of a cell is equal to E oxidizing agent minus E reducing agent. We can also use that. Or if we don't want that formula, what we can do is that we can take the species that's the reducing agent or the standard electoral potential value for the substance that is the reducing agent, then we negate the sign. If it is positive, we give negative. If it is negative, we put positive, then we add the standard electoral potential value for the substance that is the oxidizing agent. So let's see examples. We are having example 1. So in example 1, we are asked to calculate the electromotive force of a cell consisting of copper and zinc electrodes immersed in solutions of their respective ions. So we are having two half cells and the standard electoral potential value for the two half cells. So we can use different formulas. Let's start with the first formula. In the first formula, we have to know first of all which of these two half cells is the half cells for the reducing agent. The reducing agent is the one that's the most negative. So in our case, it is this one. So we are supposed to reverse that ionic equation. That means we are going to start zinc solid. Then we are going to have value. Then we are going to write zinc 2 ion. What we are doing is we are reversing the equation, 2 electrons. And we are going to write the standard electoral potential value, which is also reversed. So if it is negative, we are going to make it positive. In case it is positive, we make it negative. Then we are going to see the one that's the oxidizing agent, and that's the one that's the most positive. That means we are not going to reverse that. We are going to write the equation the way it is, the ionic equation the way it is. So copper 2 ion plus 2 electrons, arrow, we are going to get copper solid, and the standard electoral potential value, we are not going to negate it. We are going to write the way it was. So we are going to sum up these two half ionic equations. So what are we going to see when we sum up? We are going to add those two equations. How do we add? We check. Here we are having zinc solid. We don't have zinc on the product side. Zinc which is solid on the product side. So we are going to write zinc solid. So we come again on this reactant side. We are having plus copper 2 ions because we don't have copper 2 ions on the product side. So we cancel. So we are going to write copper 2 ions across. Then here we have plus 2 electrons on the reactant side, but we have plus 2 electrons on the product side. So that means this 2 electron will go with that 2 electron. Then we are done with the reactant, we go to the product side. We write the arrow. Here we are having zinc 2 ions, which is not on the reactant side. So we are going to write zinc 2 ions aqueous. Then plus. This one we have already cancelled with this. We go again the other product, which is copper solid. So we are going to write copper solid. Thereafter, what we are going to do is we are going to sum up or add these two these two standard electoral potential values. So we are going to have plus 1.10 volt. So we have calculated the electromotive force of a cell consisting the copper and zinc electrodes. That's how we are going to do it. So we can do alternatively, we can use other formula. Alternatively, or method 2, and here we are going to use the standard electoral potential value of a cell. It's calculated by E reduction minus E oxidation. So how are we going to know the one that's undergoing reduction? The one that's undergoing reduction is the oxidizing agent. So the oxidizing agent is the one that's having the most positive. So we're going to write positive 0.34 volts minus. Then E oxidation means it is the one that's the reducing agent. The other name for oxidation is reducing agent. So how do you know the reducing agent? It's the one that's the most negative. So we're going to say minus 0.76 volts. So if we add this or we put these values in the calculator, we are going to get positive 1.10 volts. That's the other way that we can answer that question. We got to example 2. So in example 2, we are told calculate the EMF for the electrochemical cell represented below. So we have aluminum half cell and also zinc half cell. Given that we have been given the ionic question for the 2 electrodes and also their standard electrode potentials. So we can use 2 formulas. The first formula, we are going to reverse the reducing agent. The reducing agent is the one that's most negative. So between these two, the one for the first one, the one for aluminum ion, is the one that's the most negative. If you check, the electrons are not the same. The first step, we are supposed to make the 2 electrons to be the same. So what we can do is, we can just multiply here by 2, then we'll multiply here by 3. Because here we have 2 electrons, we put there. Here we have 3 electrons, we put here. Then we reverse the ionic equation. So we are going to start with the aluminum, but we have a multiplication of 2. So we are going to write 2 of aluminum, which is solid, arrow. Then we have 2 times that, so we are going to have 2 of aluminum ion. That's equals plus. Then 3 times 2, that's 6 electrons. Okay, the standard electrode potential will be positive 1.66 volts. So here it was negative. What we have done is we have reversed the equation. So that means the multiplication of these two is not affected by this electrode potential value. So we go next, the other ionic equation. Here we're having 3 times zinc 2 ions. So we're going to have 3 of zinc 2 ions aqueous. So this one we're not going to reverse because it is not the reducing agent. So we are going to say plus. Then 2 times 3, we are going to have 6 electrons. Then arrow, we are going to have 3 times zinc, that's 3 of zinc solid. Then that means the standard electrode potential value will be negative 0.76 volts. This times 3 is not affected. So we are going to add these 2 half ionic equations. So we see. So let's start with the first one. The reactant side, we have 2 of aluminum ions, 2 of aluminum solid. On the reactant side, we have the arrow, we come to this other side, plus 3 of zinc 2 ions, which is aqueous. Then arrow, because these 6 electrons will go with that 6 electrons. That's why that was the reason why we were putting 2 and 3 there, so that we have equal electrons, so that we remove each other. So we're having 2 of aluminum ions, aqueous, then plus 3 of zinc, which is solid. So we are going to add this standard electrode potential values, and here we are going to get positive 0.90 volts. That's how we have calculated. Or we can use our formula 2, which we have said the standard electrode potential value of a cell is obtained by the formula E. Then we can put there, instead of reduction, we can put for oxidizing agent, E for the oxidizing agent, E for the oxidizing agent, minus E, the standard electrode potential value for the reducing agent. What does this mean? This means this will be equal to, between these two, which one is the oxidizing agent? It will be zinc ion, which is the oxidizing agent. The oxidizing agent is the one that's positive, the most positive. So between these two, this is not positive, but this is the one that's closer to the positive side. So we're going to have minus 0.76 volts. Minus. Then the start of potential value for the reducing agent is the one that's most negative. So that's done for aluminum ion. So we're going to say minus 1.66 close bracket. When you put this one in the calculator, still we are going to get positive 0.90 volts as our electromotive force. That's how we are going to calculate using the other formula. We go to so in example 3, we are told to use the cell representation below to answer the question that follows. So we have the copper half cell, the salt bridge, then we have the silver half cell, and here we have the standard potential value of the cell, which is equal to plus 0.46 volts. So we are told given that the standard potential value for the silver half cell is positive 0.80 volts. Then we are asked to calculate the standard potential value for the copper half cell. So first of all, we can say let the standard potential value for the copper half cell be X. So if it's like that, let's remember the formula for calculating the standard potential value of a cell. This is equal to, you can say, E reduction minus E oxidation. So we have the standard potential value of a cell, which is positive 0.46 volts. This will be equal to. So what is E reduction? E reduction, it is the substance that undergo reduction. So when you're writing cell representation, we said we first of all write the half cell for the substance that undergo oxidation, then we write the cell bridge, then we end with the cell representation or the half cell for the reduction side. So that means the one that they give us is the one that undergoes reduction. So we're going to say equal to positive 0.80 volts minus X, because we are looking for the one for oxidation, which is the copper half cell. So if we take this negative X to the other side, it becomes positive. X will be equal to positive 0.80. Then if we take this one to the other side, it is positive now, it becomes negative 0.46. So X will be equal to positive 0.34 volts. That's how we're going to have as our answer.